Ciao futhi. Nje kushabuka chemistry group yellow one thing pale. Asa yayi ne chemistry group ne Monica 2 days. Kana naye mwene.
Okay. So the 2019, this is a 2019 paper that was written by that intake. So on section A, from section A, there is this particular question here. So this question is actually on Matilda, your mic is on. Okay, so this question is on precipitation and equilibrium. So they are saying a solution contains this number of moles at this concentration of sodium phosphate. What is the required concentration of silver nitrate that would cause precipitation of silver phosphate? Okay, so meaning when this and this react, silver phosphate is going to be a precipitate formed here. Now, every time you are dealing with a question like this, what actually happens is that for this precipitation to happen, the initial concentrations of silver and the phosphate ion should actually be higher than that of KSP. Okay. Now, when you come up with an expression like the KSP expression, like the dissociation expression for the sort of interest, what is going to happen is that when you calculate, KSP is calculated at equilibrium, KP is calculated at equilibrium, KB or Ka for acids are calculated at equilibrium. But then if we are to calculate at Elena, switch off your mic. Thank you. Silver nitrate. So what you're going to do is write the dissociation equation for this. Okay. So when you write the dissociation equation for, okay, when you write the dissociation equation for this sort here, if you write its dissociation equation, what is going to happen is that Ag3PO4 will dissociate to give you 3Ag4 plus, and then plus 4PO3 minus. That is your dissociation equation, okay? Meaning you have to calculate for the concentrations of these at the beginning. Now, when you are calculating that, we call it as the quotient. Okay, so it being the quotient, the expression is going to be just as the expression for KSP is. The only difference is that it should use the concentrations you have initially. So you are going to write Q instead of KSP. You're going to write Q is equals to the concentration of silver nitrate raised to the power 3 multiplied by the concentration of the phosphate ion raised to the power 4. That is how your equation is going to look like. And then you now have to place in your initial concentrations. For you to find the initial concentrations, you have been given the initial concentration of this one here. A solution contains this, okay? Meaning dissociate sodium phosphate. Look at the more relationship between sodium phosphate and the phosphate ion. When you dissociate the sodium phosphate ion, you're going to have this ion, all right? You are dissociating this ion here, the top one. So sodium phosphate ion is going to give you three sodium, 4 minus there, or just three plus, and then this one is going to become 4PO. No. Sorry. This is a radical. The phosphate is a radical. Since the phosphate is a radical, for it to actually have a 4, it should be in what? It should be in brackets. Now, since this 4 is just for the oxygen, it simply means this is a 1. So when you're writing for sodium, we're going to say 3Na, okay, 3 sodium ion with just a plus multiplied by just this raised to the power 3 and not 4 phosphate, but just the concentration of phosphate raised to the power 3. Since this is not in brackets, therefore it is having a superscript of 1. Okay, so when you do that, then you're going to now place the right concentration for the phosphate and the KSP value. Then you calculate for this particular ion. So this particular question, I'm going to send what I'm talking about. Hopefully you have followed. And then you're going to actually compare the answers you are getting with the answers I'll send. Okay. And then if at all any clarities will be required and stuff, we'll be able to do that in the next meeting, that is tomorrow. Okay. Let us look at another question that was, yes. Tribe, you have a question? Tribe, you have a question? Okay, so let us go to section B. Since this is section A, meaning there will only be one section A question on this particular part. So let us quickly okay. Section B, not B1, but we can look at B2. No. Okay, so B2B. The following is a precipitation reaction. You have that. Balance the equation, write the net equation, identify the spectator ions, determine the no, not even that one. No. Calculate the minimum energy. No, that's kinetics. I think there was no big question here for this one. So just a second there. This is 2003. This one is 2008. We were from answering 2008. The first tutorial sheet we were doing, I mean, the first questions we did was 2008, I think. Let me check. B. So this is a 2012 paper. So let us look at how kinetics. Yeah, question one just straight away goes to what we've been learning, and I think I showed you guys how to answer this one the first time we met, but just for a refreshment, you've been given Kp for this particular reaction as this. Okay, so this is your Kp. When you are doing a question like this one, calculate Kp for this reaction. When you've been given this here, this is Gibbs free energy. All right. Now, you have to use the Gibbs free energy expression to find Kp. The Gibbs free energy expression is change in G with a power like with a degree there is going to be equals to negative RT natural log of E or K. Okay, so change here is equals to negative RT natural log, which is ln IN KC. You always use the concentration of so the concentration and not pressure. So you're going to use this expression to find Kc. After you've calculated for Kc, then you're going to use the Kc-Kp relationship to find Kp. And the Kc-Kp relationship is Kp is equals to Kc RT raised to the power delta N. Delta N, just delta N alone is equals to the coefficients of the product minus the coefficients of the reactants, meaning what coefficients do you have on your product? So in this case, 1 minus what coefficients do you have on the reactants? In this case, 2 plus 1, which is 3. So 1 minus 3 gives you negative 2. Therefore, your expression is going to be raised to minus 2, and then you are going to do your calculations and you will be able to find Kp. If you've understood this, if you've scribbled down anything that I'm from explaining, I think you'll be in a position where you can solve this one on your own. But anyhow, I'll send you the solutions to these ones. So phosphine decomposes to this, the reaction takes the rate, so that is kinetics. Calculate the solubility of calcium phosphide, calcium fluoride in a solution containing 0.01 molar calcium nitrate at 298.15 Kelvin. The KSP value is this at this degree. So you're finding solubility. So for you to find solubility, what are you going to do? The first thing you're going to do is you write the dissociation equation for this. Now here, section A is 5 marks. Please ensure you're showing everything because probably they'll allocate a mark to the dissociation. Okay, so calcium phosphide fluoride dissociates to calcium 2 plus 2Fl minus. So 2F minus, that is your dissociation equation. CaF2 is equals to Ca2 plus 2F minus. After you've done that, then you're going to make your ICE table. So ICE, and your ICE table is going to have initial concentration. You have calcium nitrate. Okay, I think calculate the solubility of calcium fluoride in a solution containing 0.1 molar calcium nitrate at this. The KSP for calcium fluoride is this and that. Okay, so irrespective of the question here, if you check, you've been given calcium nitrite, but this is calcium fluoride. Irrespective of what you have, we are considering calcium for the solubility, and therefore what we're going to do is the calculation is the same. So after you've done that, initially you have this, okay, but what do you have at equilibrium? Then you're going to do change here is going to be minus, then the change this side is going to be x and plus 2x. At equilibrium, you're going to have 0.01x, then minus, and then on the other end, you're going to have x and plus 2x. Now, KSP is equals to the concentration of calcium, which is Ca2 plus, multiplied by the concentration of NO3 in brackets like this, raised to the power 2. Place in your values, you have 3.9 times 10 to the negative 11 is equals to x multiplied by 2x raised to the power 2. When you do that, then look at the power here for the KSP. The power is very small, negative 11, meaning it's negligible. So you write assumption x. Now here there's even no need for the assumption because calcium fluoride does not appear in your KSP equation. So there's no need, you're just working with these here. When you do your multiplication, you're going to have 4x raised to the power 3 is equals to this value here. But you have this one's concentration, which is given here. The calcium's concentration you have, okay? Calcium's concentration you have. So where there is calcium, you're going to place that value, and then you're only going to have 4x squared this side. So 4x squared, and the answer you're going to, when you calculate for the x squared, the answer you get is the value for x. So this is a common ion effect. You are dissolving this in a solution containing this, but since calcium is present here and calcium is present there, that simply means initially you have this amount of calcium, and therefore you have to put into consideration the KSP value. So this is a common ion effect. The way you calculate here is the way you calculate every time you are dissolving something in a solution that contains one of its constituents. So we are dissolving this in a solution of this, and this solution contains this. Therefore, initially this is present. I think you're going to see this clearly when I send you the solutions to this one. So ICE table. Initial concentration of this one is irrelevant. On the other end, initial concentration of calcium is very important. So you have initial concentration of calcium, then 0.01 plus x, and this side to x. So when that goes to that, when you write your your KSP equation, since this is very small, therefore 0.01 minus, plus x is the same as 0.01. You place it there, you do your calculations, straightforward. This is also what we've done. This is also what we've done, acid-base equilibrium, a buffer containing 0.1 ammonia and 0.1 ammonium chloride. So there's this salt, there's a conjugate acid and a base whenever you have an acid and a conjugate. Whenever you have a base and a conjugate, an acid and a conjugate, it means it's a buffer solution. So this is a buffer solution. Was prepared Kb for this particular buffer is this at 25 degrees Celsius. Give the Anderson-Hassenbeck equation. The HH equation is what? You are dealing with P base. Since you're dealing with a base, it is going to be the POH and not the pH form of the Anderson-Hassenbeck's equation. So POH is equivalent to PKB plus log of ammonium salt, which is ammonium chloride divided by the concentration of ammonia. You've done that, then determine the POH of the buffer solution. POH is equals to first find the PKB from this given value. Place it there plus place where this on top, this beneath, calculate, and you'll be able to find the POH. So this is how straightforward this particular question was. Okay, so that is forces, a solution by dissolving acetone. So this is on solution chemistry. A solution containing this is also solution chemistry. Right line formulae: organic, organic, organic. Ka of a weak basic acid. So this is a lab. So you cannot be questioned on a lab you've not done. So this lab is not going to be asked, but it's an interesting lab because this lab actually makes you understand the titration graphs I talked of last time, those titration graphs. This is the lab that actually truly helps you understand that one. But since you guys have not done this one, for the meantime, it can be brought either in the test or an exam. Here, usually Onza will just test you on what they've taught, irrespective of them not teaching in a lecture or stuff. As long as it's on your course outline and during the time you were in school, you did part of it, then it will be questioned. All right. So dissociated, yeah, we have B2. So I think this is the last question we should do. Then we'll call it a night. Hydrogen sulfide, a colorless gas with a foul odor, dissociates on heating as shown below. So this is what you have. When hydrogen sulfide at an initial pressure of 1.168 bar was put into a 10-liter vessel and heated to that temperature, it gave an equilibrium mixture containing hydrogen of 0.3333 bar partial pressure. Make an ICE table of the reaction using pressure units based on the data above. So you have this. So this side you're going to put ICE. What pressure of this do you have? This is the pressure given here, 1.1. What pressure of this do you have? 0. What pressure of this do you have? 0. And then you're going to have the change. What change do you have? Minus 2x. What change do you have here? Plus 2x, and this one x just. This is 2x because of the 2 in front. This is also 2x because of the 2 in front. And this one is just x because there's nothing here, meaning it's 1. At equilibrium, now you've been given what this was just the hydrogen itself, meaning the value of X has been given. So at equilibrium, you're going to have what is this multiplied by 2? That answer subtract from this pressure. That's the pressure of this at equilibrium. This one's pressure at equilibrium is this multiplied by 2. And this one's pressure at equilibrium is just this. All right? Remember, 2H2, but here they've just said H2. There is a 2 in front. So for you to find the partial pressure of this, it's the X there. This value is for the X. So there is a 2. When you are writing the change there, it was 2X. That's why we're saying this one is going to be multiplied by 2, this one. And this one will just be that one. That's what I see it at. Calculate the Kp at that temperature. So Kp is equals to the concentration of the hydrogen ion squared and multiplied by the concentration of the sulfur, and then divided by the concentration of the hydrogen sulfide squared. So whatever answers you have at equilibrium, place them in the table, calculate for Kp, determine the value of Kc at this temperature. Kp is equals to Kc RT raised to the power delta N. Delta N is this and this minus that, which is 1. So it will just be 1 there, meaning you're just going to place in your values. Now, when you are placing in, when you place in your values, when it comes to you use, whenever you are using your gas constant, I told you you're supposed to use the gas constant of 8.3145. You'll be able to calculate the value for C. Are there any questions? Any questions?
Concerning X, when you're saying calculating for X, you said we multiply that figure by 2?
Yes. Your X, when you are showing the change, when you're showing the change, your change is actually how much is lost and how much is gained. That's why we use the letter X to represent that. But at the end of the day, when you do your calculation, it is actually the X value that you get if you paid attention to how calculations are being done. Because it might be raised to the power something, or if not raised to the power something, it just has a number. You still have to find the value of X. So whatever value of X you get, that's the concentration or that's the partial pressure at equilibrium. Now, if you look at what we've been given, they've said hydrogen gas as this as the pressure at equilibrium, meaning this is what you're getting when you solve for X. So this is the X value. So on your change there, what was here present initially? On the C section. So when you go to your change on the C section, you have what? 2X. But you are saying this is the value of X. So therefore, that's why we are saying 2 multiplied by X, and then you write the value for this particular gas at equilibrium. Beneath E, you're going to put the value you're getting when you multiply 0.3333 by 2. Is that clear?
All right. Yeah.
All right. Any other questions? Okay, so if no questions, I will send you guys the calculations done. And then tomorrow, now, this simply means that we've done quite a number of questions concerning equilibrium and stuff. So I think I'll try by all means to send you solutions early in the mornings and uploads also. I mean, the link to this particular video also. You guys go through so that when we meet in the evenings or in the night tomorrow, you will tell me whether or not we need to revisit our notes and stuff, or we have to move forward to a new topic. Now, this is what I was asking. If we are to do a new topic, are we following your syllabus as it is, or you guys will choose a topic which we have to follow or which we have to go to? Okay, so you can discuss amongst yourselves, and then you will let me know what the solution will be. Whether we follow the courses as they've been outlined in your syllabus, or we go by what you guys will agree to. Whichever agreement you make, please let me know in advance so that I can see if I'll be able to patch up some notes or just yeah, just do that. Clear.